Justin Morax from College Physics here, and we are back to do a nice little problem regarding an RC series circuit in DC. So we've got all these nice expressions. Let's put them to use in solving something out with an RC circuit. So yeah, let's just go ahead and do this, right? So here's the problem. All right, so we're going to take a resistor that has a resistance of 20,000 ohms and a capacitor that has a capacitance of 800 microfarads. And we're going to connect them to a source potential that has potential difference of 25 volts. And initially, the capacitor is uncharged, as stated, and we just want to know some things about what's going to go on here. So we could draw this out. We don't really need to, but why not, right? Got a switch, close that at t equals 0. Got a resistor, got a capacitor, there we go. So RC, E, close the switch, t equals 0, and boom, capacitor starts charging up. First thing that we want to just know is before we even close the switch, we could deduce or determine what the time constant of the system is. What is the time constant equal to? Well, the time constant is equal to R times C, which is equal then to 20,000 ohms multiplied by 800 times 10 to the negative 6 farads. What does that equal? It equals 16 what? 16 seconds. That's the time constant. See, once we know what R and C are, we have a well-defined time constant that we get valuable information from. We know then that once we close the switch, 16 seconds later, the capacitor will be 63.2% fully charged. After 2 times this, 32 seconds, it'll be 86.5% charged. If we want to know how long is it going to take it approximately to be fully charged, do 10 times this. Hey, 160 seconds, it'll be fully charged. So that is the power of defining this time constant here, because we can get a really good sense of the evolutionary behavior of the charge accumulation and the time it takes to become fully charged. So what we want to know is, hey, at what time is the capacitor 75% fully charged? Kind of typical questions. We ask it in terms of some percentage here. Well, 75% fully charged. We could figure out what amount of charge that was. That wouldn't be too hard, right? Because we know the capacitance, we know the source potential, 75% of the maximum charge, we'll just be utilizing that. Great. But 75% fully charged, this ultimately means 0.75 times Qmax. So we want to know at what time t is that equal to the charge. So we have Q of some t is equal to 0.75 Qmax. And we know that Q of t itself is equal to the function Qmax times 1 minus e to the negative t over RC. Well, there we go. Look at this. We've got ourselves this here to deal with. Solve that out for t. We don't even need to know what Qmax is. So there may become a point in time when you're asked something, you don't know what the source potential is. You don't know what the source potential is, you don't know what the maximum charge is, but it's irrelevant. It doesn't matter. It just matters what percentage of the maximum charge we want in terms of the time behavior. So what do we get with this? Well, we've got ourselves 0.75 must be equal to this part, which is the fractional value of Qmax, which is 1 minus e to the negative t over RC. So we want to solve this out for t. How are we going to get it? First, we want to isolate this exponential, right? So I'm going to kind of flip sides with stuff and say that we got e to the negative t over RC is equal to 1 minus 0.75. So what can we do with this? Well, we can shorten that up. Negative t over RC is equal to 0.25. And then we start isolating t. How are we going to get t by itself? Or at least get this term out of the exponential? And we use the inverse function of the exponential, right? Which is natural log. So we take the natural log of both sides. And we've got the ln of e to the negative t over rc is equal then to the ln of 0.25. So that's just a number, and the ln of e to the negative t over rc is equal to negative t over rc. So this becomes negative t divided by rc is equal to the ln of 0.25. And finally, we can solve this out for t, and we get that t is equal to negative rc times the ln of 0.25, which is equal to 16 seconds times the natural log of 0.25. 16 seconds because that's what rc is. And there's a negative sign there. You say, oh, you're going to give a negative time? No, that's in between 0 and 1, so the ln of that will actually be negative. And we've got 16 times ln 25 with a negative sign, we get 22.18 seconds. So then we ask ourselves, does that make sense with what we know about RC circuits? After one time constant, it should be 63.2% fully charged. Two time constants, it should be 86.5% fully charged. We're asking about 75%, which is in between one time constant and two time constants, right? Is that time in between those two time constants? One time constant is 16 seconds, two time constant is 32 seconds. Yeah, it's in between. That's it. So it makes sense. It makes sense. That's great. So there we go. And yeah, that's pretty straightforward there. So, some other things that could be asked. We could ask like, hey, what's the current in the circuit and the potential difference across the resistor at a certain time? What is I of t is equal to 40 seconds? Well, that's just going to be I of t evaluated at t equals 40 seconds. What do we know about that? Well, that's equal to I max times e to the negative 40 divided by RC, that's seconds. And what does this end up being? Well, this is I max multiplied by e to the negative 40 divided by 16. And then we just need to know, what is I max? Well, I max is going to be equal to the source potential divided by the resistance. So in the end, we have that this is source potential divided by the resistance times e to the negative 40 divided by 16, which is then 25 volts divided by 20,000 ohms, multiplied by e to the negative 40 divided by 16. And it's going to be a small current, that's okay. So we've got 25 divided by times exponential of 40 divided by 16. 1.026 10 to the negative 4. 1.026 times 10 to the negative 4 amps. It's a pretty small current. It's okay. Call it 102.6 microamps. That would be fine. 102.6 microamps. Well, that's after, what, in between 2 and 3 time constants. So, pretty good amount of time's gone by. Anyway, that's that. What if we want to know what the potential difference is across the resistor at that time? Delta V sub R at t is equal to 40 seconds. Well, that's going to be equivalent to I of t is equal to 40 seconds times R. Or we could just evaluate that, that'd be fine, but we've already got this, so we can just go ahead and use this. We've got 1.026 times 10 to the negative 4 amps multiplied by 20,000 ohms. Gives us the potential difference. 2.052 volts. There's the potential difference across the resistor at t equals 40. What about the potential difference across the capacitor at t equals 40? Delta V sub C of t is equal to 40 seconds. Well, again, a couple of different ways that we could go about this. We could say that it's equal to the source potential times 1 minus e to the negative 40 divided by 16. That would be fine. Or delta V sub C of t is equal to 40 seconds must be the difference between the source potential and delta V sub r of t is equal to 40 seconds. Well, we've already got this right there. So what would we end up getting? 22.948. You want to evaluate this? Yeah, we could do that. Why not? So we got 25 times quantity of 1 minus exponential of negative 40 divided by 16. 22.9478. Hey, it's the same thing. Equals same. Either way you go about it. So a couple different ways of solving stuff out, but these are kind of typical types of problems involving RC circuits, looking at stuff. Some other things that you can start asking about is like what point in time is the energy stored by the capacitor a certain amount or the power dissipated by the resistor a certain amount. So some things to note, not asking them here, but you could see them on an exam. Don't forget things like the power supplied to the resistor is equal to I squared times R. I is a function of time, so the power delivered to the resistor varies with respect to time. And then we've also got the energy stored by a capacitor. U sub C is 1/2 C delta V squared. 1/2 C times delta V quantity squared. This is varying with respect to time, so the energy stored by the capacitor is varying with respect to time. And it goes as the potential difference across the capacitor squared. So these are some things just to note. Hey, there are other things connected with circuitry, resistance, or resistors and capacitors, energy and energy per unit time, and just don't forget about those. At any rate, problems are fairly mild if they're kept fairly concise, but you'll find all sorts of nice little problems in homework that involve switching a switch here, switching a switch there, and you gotta figure out which way stuff's gonna happen. All right, that was fun. Until next, have a good one.